Thank you very much for the invitation. So as I said, I will give a bit of an overview about how we can extract the nuclear deformation from low energy experiments. And I've given a similar talk at the ME workshops, and it really took a very long time. So please, I can stop at any time if I run over, but please feel free to ask questions through that. So for the outline, I will first generally talk how we can determine nuclear deformation from the low energy experiment, and then I will concentrate a bit of around the mass region where a lot of interest has been recently gained from low energy side, but also from this isobar collisions and the high energy side. Then I learned that Magda will give a talk about the specific cases of ruthenium and zirconium later this week. So I will probably skip this part because she has much more and more current information to talk about that. And I will close with summary. So how can we experimentally determine the nuclear deformation from the low energy side? And this really came from first an observation of large electric quadrupole moments and quadrupole transition rates, which are much larger than what is predicted in a single particle estimate. So a quantum transition of a single proton changing its orbits gives a single particle unit, and the observation in many nuclei is that we have very many of these single particle units as a strength of a transition, and this then immediately has been interpreted as a collective excitation of the nucleus where many protons and neutrons participate. And we know that the nuclear force is non-spherical because already a deuteron has a non-zero quadrupole moment. So there's some non-sphericity inherent to the nuclei. Then experimentally observed as an example here is the excitation energy spectrum of 166 erbium. And you can see this sequence of states where the energy spacing is proportional to J times J plus 1, so the spin of the states. And this is characteristic of a quantum mechanical rotation. And a spherical object cannot rotate, so this immediately tells you that you have a breaking of the spherical symmetry and deformation of the system. So many of the physical observables of nuclei, as I will also talk about more, can be interpreted as a sign of deformation, but usually some degree of model dependence is involved in the analysis. As an experimental result, all of the nuclei are somewhat deformed. So if we extract a beta-2 deformation parameter for lead-208 from Coulomb excitation experiments, for example, then even that has a non-zero deformation of 0.055.
So I have a question. So the electron quadrupole moments and the quadrupole transition rates these are different experimental methods. My question is, do they actually access identical information, or, for example, the electric quadrupole moment is really is something about the charge distribution, but the quadrupole transition require quantum mechanical rotation, which means the entire system is rotating. So suppose the neutron and the proton have a different beta-2, will you be able to tell the difference? You'll see a difference or not?
So what we often analyze is a beta-2 of, let's say, charge, but neutrons also have an effective charge, right, in a collective model, or a nuclear deformation, which is then more sensitive to the matter distribution. So we often make the assumption that the beta of the matter and the beta of the charge is the same, but doesn't have to be identical because protons and neutrons are different.
Are there experimental evidence showing that the matter deformation and charge deformation might be different? Are there any experimental evidence?
Not within the experimental sensitivity. There's too much model dependence involved.
Okay. Well, to measure neutron distribution.
Yeah, but if you measure the deformation of the mass, then you measure the deformation of the charge.
Neutrons and protons can have slightly different deformations as follows from.
Can have.
Yeah, and for example, what is shown here is let's say in olden days, there was some kind of distinction between static and dynamic deformation, because what you measure from PE2s contains very large dynamical component.
Sure, but okay, Catherine, you want to?
Yes.
Is that I mean, but it doesn't matter if the question will be, if there's a difference, which was shown yesterday in all the DFT models, there could be up to 10% difference.
Yes.
And would you be able to tell if the deformation is big, let's say a highly deformed system like uranium, even 10% difference between the neutrons and protons, that is pretty large, because typically the physics signal goes like a beta squared, right? You know?
Yeah, so, but I think in order to really analyze it, one would have to have very, very high quality, high statistics data. I mean, I will come later to that as how to extract the beta or less model dependent than in just a rotational model. And that is really, really challenging.
Okay, but the electron quadrupole moments, does that also assume a rotational picture, right? Because it's coupling, I guess.
The quadrupole moment is
actually like a laser spectroscopy method.
Yeah, you can extract quadrupole moments from laser spectroscopy, but then not for an even nucleus.
Oh yeah.
That is the challenge there. So then you have to assume that it's kind of the same as its two neighbors, which might be a good assumption, but maybe it's also not, because we know that quadrupole moments can change from nucleus to nucleus by just adding 1 or 2 neutrons due to shape coexistence, for example. Okay, but let's say the usual way or the most simple way to relate our experimental observables to the deformation is to look at the rotational model. And I'm sure this equation has been shown many times, where the nuclear surface is expanded in terms of the spherical harmonics with the coefficients alpha, and then you assume the incompressibility of the nuclear matter or volume conservation. And then, since the dipole term doesn't matter, only the quadrupole terms are the first important ones. And then usually these parameters, these alphas, lambda mu, are redefined as the deformation parameters beta and gamma, where beta measures the elongation of a system and gamma measures the deviation from an axial shape. And for low energy physicists, this is very common, but maybe not for everybody of you. So we talk about prolate nuclei that are shaped like a lemon, so they have one long axis when the gamma is 0. Oblate nuclei that are squished down have one short axis, like a mandarin orange. They have a gamma of 60. And then nuclei in the middle with 3 axes are shaped like a kiwi. And the full triaxial is at gamma 30 degrees. So usual representation in this sector, also in many theoretical calculations, you see this. It just means that the shape changes from one of the axis to the other, from prolate triaxial to oblate. As I already said, is measuring gamma and beta is not possible, and we have to use the model to estimate the deformation from the data. And there are various observables which can be used for that, and they will go in increasing complexity. So the simplest observables for spectroscopists like me is just to measure the energies of states. And in a rotational model, the energy sequence, the energy spectrum, is given by this factor of J times J plus 1, which is the angular momentum of the states in a band, and this K is the projection of the angular momentum onto the symmetry axis of the ellipsoid. And here you can see again experimental data of one nucleus which has 3 different bands which are characterized by different deformation. This parameter I here is the moment of inertia, And if we assume a rigid ellipsoid, then in first order, the moment of inertia can be written as just the mass number, the radius, and the deformation parameter. So by increasing the deformation, the energy spacing of these rotational bands gets smaller and smaller. And of course, this whole thing assumes that the moment of inertia is constant along such a band. And the calculated levels here in the rotational model are shown by the red, and the experimental values are the black line. So you can see that this nucleus behaves very well like a rigid rotor. Of course, then one has also superposition of vibrational excitations and other things which complicate the excitation spectrum much, but at least what you are interested in, my understanding, is the shape of the ground state only, and you're not so much concerned with the shape coexistence or different shapes within one nucleus existing.
So the moment inertia changes, right? Once you couple with vibration. Yes.
So in this case, these are three different bands with different moments of inertia.
Why is one called a gamma band and the beta band? What is the origin of that one?
Okay, so these are vibrational excitations on top of the deformed thing. So it is the vibrating of a axial deformed thing, so like a football which vibrates, which gives rise to this gamma vibration, beta vibrational band, and gamma is vibrations in the gamma degree of freedom. So it's not a static, in this case, it's not on this assumption, it's not a static gamma deformation, but it's a vibration of fluctuation in the gamma degree of freedom.
Rigid system, right? So it's vibration because it's rigid.
Yes, and then each of the vibrational states can rotate. So if these superpositions of the different motions of the shape. Okay. So if one then looks at actual experimental moments of inertia, which can be extracted from the measured excitation spectrum, so one can extract the moment of inertia. This is a plot where the experimental data is shown by all these symbols and the lines, and it's compared to extreme assumptions of this rigid body in blue, and then irrotational flow by this red line here. And you see that all of the experimental data is approximately in the middle of that with some variation. So the nucleus is neither rigid nor liquid. So yes.
Formula. Is this like some theoretical motivation behind this?
Sorry, I couldn't understand you.
Experimental, you have this formula there. The formula on the left hand side.
Okay. So this is just an approximation. So the experimental data on average is best reproduced by this formula. So this is just a phenomenological parameterization of the moment of inertia as a function of mass and
so the rigid is if it's rigid, it's just linearly proportional to beta, but then experimentally you always prefer beta squared.
Yeah, and also the mass dependence is different. You see, there's some mass dependence here also. Okay. So then if one assumes a rotational model, then the spectroscopy of the first few excited states is enough to get a good idea about the deformation of the nucleus. So the excitation energy of the first 2+ state, if it's very low, then this indicates a collective nature, so deformation. But what we typically look at is this R4-2 ratio, so the energy ratio of the 4+ state to the 2+ state, which in the rotational model with this J times J plus 1 factor comes out to 3.33. And for a purely vibrational state, so a sphere that vibrates, this comes out to 2. So in the plot, you can see the whole nuclear chart, the excitation energy of the first 2+ state. And on the right side, this R42 ratio, and the behavior is exactly mirrored. So large R42 corresponds to very low excitation energy. So deformed nuclei are in the region of blue here, or red on the other side, and the magic spherical nuclei are along the magic numbers here. And yeah,
Magic nuclei, the ratio equal to 1 or close to less than 2, right? I just look at the color, the magic.
Magic nuclei for the R42 have a ratio of less than 2, around 1, because it's just a pair breaking thing. So the excitation energy of the 2+ and the 4+ state does not differ much in the magic nucleus. So this is like maybe the simplest observable is the excitation energy spectrum, but another simple observable which is also directly related to ground state properties which are of your interest are charge radii, and by a detailed spectroscopy of the atomic spectrum, one can draw conclusions about the size of the nucleus. Because the size or the charge distribution of the nucleus itself affects the atomic spectrum. Of course, with very high resolution, one can only resolve these differences. And the mean square charge radius of a deformed nucleus, then there are 2 components. One is just as a function of mass number, the charge radius rises just because in a liquid drop model, the size of the sphere grows. And then there's a second component which is due to the deformation. So in the plot is the change in the charge radius, the relative change in the charge radius for a certain nuclei shown, and it's always relative to this magic number 126. So there's a smooth decrease of the mass of the radius with the mass. So for lighter nuclei, the charge radius is less. But you can see that here, for example, for the polonium, at a certain point, the charge radius increases, even though the nucleus should be smaller because it has less protons or less neutrons. So this is a sign of deformation because the apparent size of the nucleus grows, even though it has less A. And experimentally, these charge radius can be determined from isotope shift. So that's the difference in optical transition frequencies between 2 isotopes. So from atomic spectroscopy. For stable nuclei, this can also be determined in electron scattering. So the classic Hofstadter experiment. And matter radius can be extracted from interaction cross-section measurements. So these are maybe similar to the experiments that you are discussing in heavy iron, is that the interaction cross-section of the nucleus is related to its matter radius.
For the second formula, why it's 2 phase, it's not 3 phase?
Oh, he's asking the.
Yeah.
That's
The second, oh no,
This one?
what's the difference?
I would say because it's a typo, I have to check. I know it's a differential. It's
You take a derivative of the
it's
A.
a derivative. Sorry.
Yeah, one should be a bit careful with use of this mean square charge radii.
Yes.
Because if you go, for example, to atom mercury isotope, there is a kinking charge radii about shell closure 126. And it is not related to the change of the deformation, it is related to the orbital which is occupied in
Yes.
our shell closure. So This
Yeah,
form
this
approximate, let's say, give some idea, but not should be used, let's say, as a precise measure of the deformation.
yes, I mean this is what you would expect here. The next shell is filled, so the nucleus grows. But I was going towards this increase of deformation, which is shown here.
There's something
This
just
is mid shell.
so I'm sorry. Can you go back just one slide? I was thinking while you were talking. So for the magic nuclei, you're seeing that the excited states, those are not collective states, right? Those are just non-collective states, or this.
Yes.
What do you mean by magic? Not magic. Let's say lead. You can measure the 4+ and 2+. Those are
Yes.
basically not. Those are basically those are the new excitation energy is so big it start to. I mean, what kind of excitation are those for the
A single particle excitation.
single particle excitation?
Yeah. So you have to promote 1 or 2 nucleons to the next orbital.
Oh, okay, so they are still bounded, but they are really single particle.
Yeah.
Right. Okay, thank you.
Okay, and then as you can see here, very interesting in Mercury, the charge radius kind of jumps from isotope to isotope. And this discovery of this shape staggering created a lot of interest in this region here, because by just adding or removing 1 neutron, the shape changes between spherical and deformed. And later this charge radius was also measured for long-lived isomeric states, so an excited state which has a lifetime long enough that you can do optical spectroscopy on it. And it turns out that the excited state is spherical while the ground state is deformed. And this phenomenon of shape coexistence is really coming up at many cases of the nuclear chart. So there can be shape inversions and also a nucleus which has 2 states close in energy which have very different deformation. The more complex observable is then the quadrupole moment, which has a very simple definition, just as the charge from the charge density. And if one writes this quadrupole moment in terms of this beta 2, in lowest order, the quadrupole moment is proportional to beta 2. What is important is what is observed in the lab, because what we observe in the lab is the spectroscopic quadrupole moment, which is related to the intrinsic quadrupole moment by this formula where I is the spin of the state and K is the projection on the symmetry axis. So if you have a spherical 0+ ground state, then the spectroscopic quadrupole moment is always 0, okay, because I is 0 and K is 0, and the same applies to 1/2 state. So this quadrupole moment cannot be obtained for even nuclei in this way.
And also for some of the odd one you cannot. If a
Yeah.
you also cannot.
Yeah, if it's 1/2 you can also not, but there are not so many. I mean, even nuclei is much more than half of the nuclear chart. Spin 1/2 is some of them, but not all of them. Extracted if I is larger than 1/2, it can be measured again from atomic spectroscopy, and this again uses the coupling of the electrons to the nuclear field, and this time on the magnetic and dipole and electric quadrupole moments of the nucleus. So essentially the energy that is measured in atomic spectroscopy depends on the total angular momentum of the nucleus and the electrons, and then the nuclear angular momentum and the electron angular momentum, and it also depends on the magnetic and electric field gradient of the electron at the nucleus. So again, this is measuring this absolutely is challenging, but because of that, or it has to be calculated quite precisely, this electric field gradient at the nucleus. But spectroscopic quadrupole moments can be extracted again from atomic spectroscopy. But it is not an easy measurement, and it only accesses the ground state properties. And these quadrupole moments, as I already pointed out in the beginning, were also one of the things that motivated this whole description of the nucleus as a deformed shape. And I have quoted here something from this paper from 49, where the large quadrupole moments that have been experimentally observed. The quality of this figure is very bad, but you can see that for some nuclei, there's really huge quadrupole moments observed, where one in the nuclear shell model only predicts very small values, very close to zero. And this can only be explained that by including the core. So unlike in the shell model where you only treat the one or two or few nucleons outside of the core, the polarization of this core has to contribute. And this itself, these authors call, is against the definition of the shell structure model of the nucleus, or the shell model. So this is one of the motivations which led to collective models of the nucleus. So the observable, which probably gives best access to deformation, is reduced transition probabilities. So these B values of the reduced transition probabilities are measured. There's a square missing here. Measure the overlap of initial and final state. So if we measure a large B value, this means we have a similar structure of the states, and these matrix elements here, they are related to intrinsic quadrupole moments. So if the quadrupole moment or the quadrupole moment can be accessed through a measurement of the BOV2 value through these formulas. And then again, if you apply the rotational model, the BOV2 value, the transition strengths can be related to beta. And the experimental observables, the BOV2 value, can be obtained by essentially measuring the lifetime of a state. So by determining the lifetime, the energy, and also the conversion coefficient of the certain transition, we can get access to the transition probability, which relates in the rotational model to the beta 2 value. Okay. So how can one obtain the transition strengths from experiments? So depending on the lifetime of states or the widths, there are different experimental techniques. Indirect methods essentially measure a cross-section of the excitation process. Or if the width is large, then obviously one can also measure the width of a resonance and extract the lifetime from that. And then there are more direct methods which range from electronic timing. So this is really just a start and stop measurement between a reaction populating a state and its decay. And then there are various methods which make use of Doppler shift techniques. So the gamma rays are emitted in flight and therefore give some information about the time or how the nucleus flies through space. And similar blocking techniques make the use that, you produce in flight a state at some point and you measure it at some distance later, and by varying this distance, essentially you can extract the lifetimes. If we have a look again at the whole nuclear chart of all the nuclei where the BOV2 values are known, then this is shown on the right. We see a very similar behavior between the BOV2 values and these R4-2 ratios that I mentioned before. So now red areas where R4-2 around 3.3, indicating deformed rotor, now correspond to areas where we have transition probabilities of 100 or more Weisskopf units. So this Weisskopf unit is the single particle unit. It's an estimate of what is the strength if a proton changes its orbit. So again, the magic nuclei where we have single particle excitations, we have BOV2 values around 1 Weisskopf units, while collective nuclei, that means that essentially all of the nucleons participate in this excitation. This is not as strict as the 100 nucleons participate. It's more an estimate of the strength. So then one can also relate this back to what I said earlier, that already the energy of the first 2+ state tells you a lot. And there's a nice correlation between the BOV2 value and the excitation energy of the first 2+ state, which was figured out by Grotzins in 62. However, these energies alone are not sensitive to details of the wave function. So more experimental observables we get from the BOV2 values. And I have some more examples then about that later in the talk.
So what do you mean by energy are not sensitive to the detailed wave function? It just what do you
Well, okay. If I change the single particle energy, I change the energy, but I can have the BOV2 value really tells me the overlap of initial and final state. It's really sensitive to the wave functions.
So this wave function, do you refer to like collective wave function or just single particle?
Yes, I think this is in terms of the single particle wave functions. Okay, so this is essentially the same information as on the last slide, but plotted a bit differently. On the x-axis is the BOV2 value in Weisskopf units. So this is the single particle estimates, how many nucleons participate in the excitation. And here it's shown the R4-2 ratio against this BOV2. And the limits of the spherical vibrational nucleus at 2 and the deformed rotor at 3.3. And the spherical nuclei are, the magic nuclei are shown by orange dots. So they have very small BOV2 values. And generally R4-2 ratios less than 2. There are some exceptions here, but you should not be concerned about them too much. And then there are the rare earth region, which many nuclei in this region are very well deformed, and they are marked in green. So you see that they have BOV2 values of around 200 Weisskopf units. The mass number around that region is around 150, 160, 180. And the R4-2 ratio is very close to 3. So again, the correlation of the BOV2 and the R4-2, it gives good indication about the deformation of these nuclei. And lastly, I show here some heavy and super heavy nuclei, which are the most deformed nuclei that we know of. And then in the other panels, the same information is shown now, the BOV2 value scaled by the mass. So this is a measure of collectivity. So larger than or values around 1 are strongly collective, and 0 is single particle like. And on the right most panel, instead of the BOV2, I extract in a rotational model the beta from the BOV2. And for the deformed nuclei, this works very well. So you see all the ones which are at an R4-2 ratio of around 3.3 have better deformations of around 0.3, which is strongly deformed nucleus. But this method also gives very large beta values for nuclei where we actually know that they should be spherical, or we believe that they are spherical from other observables. So this plot here, on the most right, makes an assumption of a rotational model, which is maybe not applicable to all of these cases.
Are those mostly light ions? Or light?
These are mostly light, yes. A lot of them are light, yes.
Okay,
But there's also some cases where it's a traditional magic number, which then has, due to some shell evolution and some like changes in the nuclear shell structure, turn out to be not magic nuclei.
so I wonder if there's such plot for, let's say, mass bigger than 100, how this will look like for this plot.
Yeah, okay. I only singled out the rare earths here now, but of course one can look at this for specific masses. I can prepare this if you want.
The light ones, of course, it's harder to discuss deformation, and also
Yes.
heavy ion, right?
But they are not all light ones. I mean, there's also the thin isotopic chain, lead, and so on. There's also, one has to look case by case. I mean, I would just want to highlight here the really deformed ones. I don't want to talk about these ones because the beta of these two is for sure not this large.
Yeah.
So it's just a warning. I mean, this formula is very nice, but it might also produce betas which are unreasonable.
And this only based on the transition from 0 to 2 plus.
Yes, yes.
Let's see the quadruple invariant estimate, right?
Yeah. No, this is just the BOV2 of the first 2 plus state. We come to the quadruple invariance later. So I'm trying to go here by increasing complexity in the observable. The quadruple invariant is extremely complex to analyze and extremely difficult experimentally. Okay. So then how do we experimentally determine these BOV2 values? So we use or often use Coulomb excitation as a probe of collective shape degrees of freedom. And this works by colliding our nucleus of interest in the Coulomb field, or colliding it with the Coulomb field of a target. So in this time-dependent field that this nucleus sees as it passes by, it will essentially absorb a virtual photon and become excited. And by some simple perturbation theory and multiple expansion, we can relate the cross-section for this excitation to this reduced transition probability. So this makes this experiment relatively easy. If you have it all under control, you just have to measure the excitation cross-section, and then using this simple and well-established Coulomb excitation theory, you can derive the BOV2 value. In the experiment, you want to maximize the electric field, so you use a high Z probe. So, for example, a lead target, or sometimes not so high Z, but nice is thin nuclei, because also these two are proton magic numbers. That means that their own excitation does not matter so much. So in this process, of course, both of these partners are excited. So if one of them is a magic nucleus, which has a very small BFE2 value, it doesn't disturb you so much. Now, the devil is in the detail, because in this case, you assume that you have pure Coulomb scattering, so you're very peripheral and you do not touch, the two nuclei do not touch each other, or there's no interaction by nuclear forces. And this, in the experiment, of course, you cannot avoid. So you have to either by a clever experimental setup and cuts on scattering angle, eliminate the contribution from these nuclear processes, or you have to analyze them in combination so that you have the interference of nuclear and electromagnetic excitation. But it's a rather well-established method, and it gives you access to the BFE2 value rather easily. One of the assumptions here is that this whole process is a one-step excitation. Okay, so what I just described assumes that you have high binary energy, which is above the Coulomb barrier, and that you have a single-step excitation from the ground state to the excited state. Then the only thing is that you have to care about are these nuclear excitations and some reaction model, and you can get an uncertainty of a few percent for the BFE2 value if you have nice statistics. And then you can make use of this relation. But usually, or at many experimental facilities and also traditionally, you have much less beam energies, which are at the Coulomb barrier energies, which means that the interaction time between the projectile and target is much longer, and therefore you can have multi-step processes. And this is depicted here on the right side. You can, for example, excite first another state and then go down to the state of interest. So this can be two-step excitation, so you can make two steps up, but you can also, of course, de-excite in this process. So this, first of all, allows you to extract also BFE2 values for other states. So here's an example shown where it's the cross-section for the excitation of 2+ state, which goes by this one-step excitation, and the 4+ state, which requires 2 steps because you need to, well, the angular momentum of transfers is, of 4 is strongly limited, so you can only do two excitations. But then you also have the case that, you know, you have this so-called reorientation effect where you excite a state, but then you have an interaction of this state itself and a redistribution of the magnetic substates within this. So this is also a 2-step process. And this is actually sensitive to the static quadrupole moment. So the cross-section changes depending on the prolate or the oblate nature of the state. And the example here is shown in the data. The data is the black crosses. The blue curves assume static quadrupole moment of 0. And then we assume either oblate or prolate in green and red. And you can see that the data is really sensitive to that. And the cross-section as a function of the scattering angle can be used to access this quadrupole moment and its sign. So not only the magnitude, but also its sign.
So this reorientation effect, what do you mean in detail? So you when you're excited to one of the substates, right? Let's say E2, there's a 5 states, 5 projections, right? Do you mean you excite one of that, one of the 5, and then there's
a certain distribution.
Okay.
Yeah.
So there's a preference to excite one of that state, right?
Yes.
The reorientation effect, how that influence the cross section?
So I mean, I have another slide on this exact process here as well, but it's a kind of a virtual excitation of the state in itself, right? It's you can reorient the state.
Right.
You change the magnetic substate distribution in the second step.
But that changes your overall cross section.
This changes my cross section. This is shown here by the different lines. So if the QS is negative, the cross section goes down. And this is plotted here as a function of the scattering angle, because these processes for scattering towards the back, the interaction time is even longer. So if a collision and the probe goes back, then the interaction time is longer, so it's stronger at larger scattering angles. Maybe it becomes a bit more clearer on this plot, because typically the way that this is analyzed is in such a plot where you show the transitional matrix element and the diagonal matrix element in this two-dimensional plot, and the cross section, if you don't observe it differentially, but you just measure the cross section, not as a function of scattering angle, then the cross section will depend on both of these, and on top is plotted the chi-square as a function of these two parameters, and you see that there's a white band which reproduces the experimental values. So you can either have a larger diagonal one, larger positive diagonal one, and a smaller BOV2, or a larger BOV2 and a more negative diagonal moment. So the
So the diagonal is what you call the reorientation part, or
this is the quadrupole moment.
Just
the quadrupole moment of the 2+ state.
And which is responsible for your reorientation, right?
This one here. So if you just measure the excitation process from the ground state to the 2+ state, and you just measure the cross section of that for a low energy collision, then you cannot determine the transitional or the diagonal quadrupole moment, because they both correlate like this. So in this type of experiments is that one uses different observables, namely the lifetime from a measurement of really the time, decay time, which is only related to the transitional matrix element. This is shown in the bottom plot. If you know experimentally that the lifetime gives you this transitional matrix element of 32, then you can make a cut, and this then really defines you also the allowed area for the diagonal quadrupole moment.
This correlation line is from the theory, or this is the experimental data?
So these dashed lines here are experimental data on the lifetime.
Right, but this correlation, this band, this 2D contour, this band is model, or this is the?
This is experimental. The experimental cross-section depends on both of them.
Okay.
So this is the chi-square between the experimental cross-section and the reaction model calculation.
Okay.
Assuming different values for the two.
So the BE2 is you measure the square of this where y-axis, right?
Yes.
And you only know you don't know the sign. Okay, I mean this is all positive, but okay.
We don't measure BOV2. We extract the BOV2 from the measured cross-section.
Okay.
So this is one of the ways to access actually quadrupole moments, and from atomic spectroscopy, quadrupole moments are only possible for spin larger than 1/2, and only for the ground state, or if it's an excited state, it has to be long-lived. So long-lived means milliseconds or so. Yeah? And the lifetime of typical excited states in nuclei is picosecond, femtosecond. Right? So there's no way to do atomic spectroscopy on these. So this Coulomb excitation method is the only way to access the quadrupole moments of excited states. The sensitivity depends on the complexity of the level scheme and the statistics. And I'm sure that Magda will be able to tell much more about that in her talk. And I will not talk at all about the E3 moments, but I know that there's some interest in that, and they can also be accessed through Coulomb excitation. So you can, of course, also excite a 3- state through E3 excitations with much less probability. Okay.
Oh, can I just, I'm sorry, but if you go back one more, this, you have the 3 curves on the left and the right. What are those again? I mean, they have different sign.
So the blue one assumes 0 quadrupole moment.
Okay.
And then green and red assume prolate or oblate deformation. Green is always the best fit to the experimental data, and red shows the opposite sign.
Oh, so this suggests there is a deformation, quadrupole deformation, because they have a best fit. And you also
Yes.
put the sign. Right?
Yes.
And
Yes.
this is what? This is an oblate or prolate?
This is prolate.
Prolate.
Yes. Yeah, sorry, there's no reference here. So, okay. So what I've said so far is that the deformation is very difficult to access, and there's always some model dependence. You have to assume a rotational model. If you extract these from the Coulomb excitation, you have the issue that you not only excite the first 2+ state, but you excite other states, and you have to consider them. So it's not very easy to extract them. And there's one observable or a quantity, which are these quadrupole invariants, which provide a model independent measure of the nuclear shape. And this quadrupole invariants relate to the charge distribution in the intrinsic frame. So the charge distribution is parameterized or written as these invariants, or the values of Q and delta, and they can be accessed. So this Q invariant can be accessed by, let's say, for the ground state, by taking loops through here. So you from a state you excite to an intermediate state, and you go back to the ground state, and you have to sum this over all of the states in the nucleus. Of course, there are many states in the nucleus, so usually experimentally, at least, you have to truncate this at some level, but higher states only contribute less and less, as far as we know. And you can look up this reference very nicely, summarizing the method and also the sensitivity and the issue of truncation in the experiment. So you have to make these loops, and this gives you this value of Q square. But you can also go through 2 intermediate states. So you go, for example, from the ground state and then to the next state and then back to the ground state. And if you sum up all of these possible loops involving 3 transitions, where there can also be this type of self transitions, then this gives you access to this invariant Q3 cos 3 delta. And they can be related to the deformation parameters of the Bohr Hamiltonian, and this Q square is related just simply to beta square, and the delta is equivalent to the gamma. So now you just have to measure experimentally all of these matrix elements and sum them up, and you're done. The only problem is that there are many of them, and they all have signs, and experimentally it's very challenging to extract the signs of all of these matrix elements.
For the simple Q square, the the left column, the Q square average. So the BE2 is just measure one of that, right? One of
the BOV2 measures one of them, yes.
But even with that, you can still extract the beta 2. The question will
yes.
be, this must make assumption. Is this like you assume a rigid
Yes.
figure, so you only need the
Yes.
first transition that represent the full information?
Yes.
But in reality, suppose the exact states have a different shape, the Q invariant method still works, but the transition
Yes.
method will not work, right?
Yes. 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 I mean, if I just have this one, I mean, I'm basically making the assumption that this transition rate has any relation to the shape of the ground state. I mean, this is absolutely not given, right? So by summing them all up and calculating all these transitions, I can make a statement about the shape of the ground state. Okay. So this is already challenging to extract, let's say, beta and gamma from these measurements. But what is then even more interesting is to look at higher order of these invariants, which gives access to fluctuations of Q and of delta. So then you have to, this is what we had before, just the 2 loops and then the 3 loops. And then if you want to access the fluctuations, the variances of Q, then you have to make all possible loops involving 4 transitions. And of course, it just gets more and more complex, right? Because you have to have this and all of them until infinite. So it's extremely challenging to do that. And if I remember correctly, I personally only know one example where this has been analyzed in great detail, but there are maybe a few. So because there was yesterday a question about the gamma degree of freedom and why the gamma degree of freedom is not so well known, I added some slides which now talk a bit about the gamma deformation.
So I remember that there's a measurement that determines the gamma
Yes.
Angle like 15 degrees for some species.
Yes.
Summation, but it's not complete summation, right? But
no.
What is your opinion? Like, are those really robust? What I mean, they did this quadruple. They consider this Q cosine 3 delta. They did a summation. I remember.
Yes. This comes here. So what they did in this measurement is to make these summations of 3 states, which gives you this cos 3 delta, and then you have delta, and then you have gamma. This is fine, but gamma alone, I think, does not tell you anything very much, because what you actually need is to know whether this nucleus is rigidly deformed. And this is, I think, what you would extract from your heavy ion collisions is the nucleus rigidly deformed in its ground state, or whether it is gamma soft and the potential does not depend on gamma. So actually, this is one of my questions and my conclusions. Are you sensitive to the nature of gamma?
I think so.
You
But-
think so? Okay. Yeah, you're sensitive to everything.
Depending on the level, yeah.
It's not clear to me that we are only sensitive to rigid deformation.
We know we are sensitive to all fluctuations.
Yes.
But yeah, but intrinsically we are doing multi-particle correlations, so which are kind of, I think it's more related to this Q invariant.
Yes.
And therefore, I mean, we don't need to do the summation because it's automatically part of the particle correlations. But of course, it's also challenging to decompose this, like the mean and the variance, right? For example, but I think it's doable.
So regarding the triaxial degree of freedom, there's a very simple approximation, which is a Davidov-Filipov model, which is a gamma rigid rotor, so a stable gamma deformation. And this predicts, as a function of this gamma degree of freedom, the excitation energy spectrum. And a signature of triaxiality is this low-lying gamma vibrational, or so-called gamma vibrational band, which is the second 2+, which is this orange one, as a function of this gamma degree of freedom, comes down strongly in energy, and for maximum triaxial nuclei goes below the 4+ state. And then on the right side is the relative transition probabilities, so the BOV2 values for the decay of this 2+2 state. So you see, if you compare orange and green, that the 2+2 state for maximum triaxiality prefers to decay to the ground state band 2+ state and not to the ground state directly. So by looking at these two properties, you again can take simple observables of excitation energy spectrum or BOV2 values and try to assess the gamma degree of freedom. But there's one issue, there's a second simple approximation of, let's say, triaxial deformation, is that the potential is independent of the gamma degree of freedom. That's completely soft. And the plots here show you, as a function of the gamma degree of freedom, that there is not so much difference between those models. So looking at excitation energies alone is not sensitive to the nature of the triaxial deformation.
You have models, those are not models, right? Yes, those are different models.
Yeah, these are the two different models. This is the, sorry, there's no label. The right one is this Willits-Jean model of the gamma softness, and the left one is the same as this one, this Davidov-Filipov model of the rigid rotor.
But this model independence, because they all assume the rigid.
No, the gamma soft does not assume rigid.
Okay, so different gamma soft model, and they all have the same band structure. That's what you mean.
Yeah. So just to illustrate this is one example, which is maybe the one that you talked before about, is where this has been really studied very well. This is germanium-76, which the interest in the was that this is a neutrinoless double beta decay candidate. And the energy ratio of the 4+ to 2+, the observable that we have used to assess the deformation, is experimentally 2.51. This gamma soft model predicts 2.5, and a rigid triaxial one predicts for a maximum triaxiality 2.67. So experimentally, it's not so easy to distinguish between those two, because we probably know that it's neither of them. These are just two extreme limits of triaxial models. So we look at the transition probabilities, and this is the same as shown here. Is how does this 2+2 state decay? Does it decay to the 2+1, or does it decay to the ground state? And you see that for maximum triaxial deformation, this predicts that the decay to the ground state is forbidden. But this is also in the case of the gamma soft model. So both of the models predict that this BOV2 ratio is 0. And in the experiment, it's not 0, but it's very small. So based on all of these observables, we cannot distinguish between rigid triaxial and gamma soft. So then there's one difference of the models, and this is in the so-called stage parameter. So this measures the energy differences in the gamma band. So is the 3+ state closer to the 2+ or to the 4+, for example? So this is, again, here you see that these states here are from the gamma band, so orange, green, purple, and pink, and you see that they group together. So 2 and 3, and then you have 4 and 5, which group together. So this is expressed by this difference of these excitation energies. And this is plotted here for different nuclei, germanium, selenium, some krypton isotopes. And you see that all of the nuclei except for the germanium 76, so let's say, go up, down, while the germanium goes down, up, down, up. So the phase is opposite. And actually the phase, again, at the bottom is just the germanium. The phase of the staggering of going down, up, is consistent only with this rigid Davidoff-Filipov model. So for maximum triaxial deformation, you would have so down, up, but with much larger amplitude as what is observed experimentally. So you see, experimentally, the staggering is on the order of, let's say, 0.1 or so, and this prediction predicts staggering parameters of 2. So the ordering of the states, or the staggering of the states, is consistent with a rigid triaxial shape, but it's much less pronounced. So this is the first indication that we have rigid triaxiality here. The other thing is that we can access this thing through the quadrupole invariance. But again, this is experimentally extremely challenging, and this paper from 2019 is a very nice example of what you all need to do in order to get the experimental information. So this shows you the spectrum of what has been measured in the experiment. So they collide germanium with lead and measure the gamma radiation corresponding to all these different transitions. And in the table here, you can see that they can extract matrix elements, E2 matrix elements for 20 or so transitions, but also diagonal ones with their respective signs. And in the level scheme, you can see that what was known before that experiment is shown in red, but they were able to extract matrix elements for all the transitions which are shown here. And this is really a very complex data set, because all of these transitions are linked to each other. So more cross-section observed for this transition is affected by all the other states which are connected to it. But then with this amount of data, so let's say, I don't know, 20, 30 data points, one can try to calculate these invariants for not only the ground state, but also for other states. So first, what is shown here is the quadrupole invariant and their fluctuation in the ground state band and in the gamma band. And one can see very nicely that they are almost independent, or basically independent of the spin. So this points back to the rotational behavior, and maybe says that this rotational model is very good in this case. So the deformation is the same for all of the states, and also for the same for the states in the gamma band. And this corresponds to a quadrupole deformation parameter of 0.28. And the fluctuations are small. I mean, there's also experimental error bars in there, so one cannot really only see this as a, so you have to be careful that the magnitude of the fluctuation is small, but the experimental uncertainty is also sizable. So not in every case one can make really precise statements, but it seems that one has a well-defined, rather well-defined beta or quadrupole deformation.
In order to have the sigma Q2, you need all these four transition, four connecting the intermediate state. You need the four of them, right? Four legs.
Yeah, for this one you need 4.
Yes, so they have enough data for this.
For this one you already need Q4, and Q4 already has these 4 transitions. For the other one you need Q6, which is more challenging.
But they have enough data to actually do Q4 already. Q to the 4.
They have data to do Q4. They also then extract this cos delta 3, which is sensitive to the nature of the triaxial degree of freedom. So if cos 3 delta is -1, then this is oblate. So oblate is the Mandarin orange. If it's 1, then it's prolate, the lemon, and the triaxial are in the middle. So they find that again both the ground state band and the gamma band are consistent with a triaxial deformation of 27 degrees or 25 degrees, and it's roughly independent of the spin. But the question which is still not addressed is this triaxial or is it gamma soft? And to address this question, you need to have the Q6 invariance. And in this experiment, because they have so many matrix elements, they actually are able to get some kind of information about the fluctuations of cos 3 delta. So again, this needs summation over all states, but the product of 6 matrix elements. And the experimental data is shown again here, and they find that these 3 states where it's possible with the experimental data to assess this value is that it's consistent with rigid deformation. Because it's really quite nice sensitivity here. The gamma soft would have a much larger value, of 1. So it's all consistent with 0. And to my knowledge, this is it's one of the very few cases where this analysis has been done in such great detail. And
truncation won't be an issue, right? I mean, they measure many states, but they still need to truncate somewhere.
Yeah. I mean, they need to truncate because they only have these matrix elements.
What is the uncertainty associated with that truncation?
So, I mean, regarding this truncation, I should have maybe put it somewhere. But if you look in this paper, there is a kind of a sensitivity study where it's a function of the number of states that are included. I mean, this is based on shell model calculation. In a shell model, you can calculate 100 or 1,000 or 10 states, and you can make this analysis and you can see how the value changes. And also in this case where there's no reference given, but this is Sync 72, and I made this analysis, and once you include, let's say, 10 states, then you have most of it in there. So whether you have 10 or 100, I think doesn't matter. Of course, the theorists will disagree with me, but I will not be able to measure 100 states. Okay, so this is basically my conclusion of this part, is that to decide on the nature of triaxial deformation, whether it's rigid or gamma soft deformation, is extremely difficult to assess. And therefore, so one of my questions at the end is how sensitive you can be to that.
This measurement, you have 3 data points.
Yes.
For each state. Well, different. What are those?
Yeah. Okay. So these are how the experimental summation is carried out. So I cannot tell you the detail now, but it's like whether they include certain spins or not.
Yes, thank you.
Okay. I guess I'm already over time again.
Yeah, continue, please. It's okay. It's okay. We will stop somewhere. How many slides you have?
I have a couple of more about this shape transition and shape coexistence stuff, but you can also
Continue unless if people want to stop, we stop. But we have 2-hour lunch break, which is a long time.
Oh, okay, I see. Okay, so I can tell you a bit more about this nuclear deformation and changes of deformation in this region, because when I was initially asked to give such a talk for this Emmy workshop, it was all about these isobars, and they are especially zirconium 96 has attracted a lot of attention in the last, let's say, 5 years or so, because of its shape coexistence and shape transition things. So that's why I briefly had summarized how nuclear structure changes in that region. But maybe it's not so relevant to the question of either these isobar collisions or the other work that you hope to do with heavy ion collisions. So, but okay, I mean, you just interrupt me when it gets too boring. So as I said, in this region around mass 100, there's lots of exciting things happening, and there's lots of signs of sudden onset of deformation. So this is shown here as a function of the neutron number is shown on the left side, the 2 neutron separation energy, and on the right side, the charge radius. And then what is indicated here is neutron number 60. And on the right side, I show the expected filling of orbitals according to the shell model. And there you can see this kink at magic numbers where the next orbital is filled and the size or the apparent size of the nucleus rises. And then in a 2 neutron separation energy, this determines how much energy is required to remove the neutron. So this indicates how strongly bound the system is. You can see at neutron number 60, the neutron separation energy rises. So this is interpreted as additional binding coming from deformation. And then this is also related here on the right side to this jump in the charge radius at neutron number 60, where suddenly you go from here to here, while you still should fill the same G7.5 orbit. So this, again, these two things are indications of deformation, but it's a very localized feature in the sense that if you plot this now for other isotopic chains, you still see it. For example, in strontium, you see a very similar behavior, or yttrium, and the same jump in the charge radius at neutron number 60. But then when you go out of this region and look at molybdenum, ruthenium, krypton, it's all very smooth, and there are no jumps neither in the charge radius nor in the separation energies. The zirconium nuclei around neutron number 60 are really an island of deformation. And if you remember what I said before, but also look here is that there's certain isomeric states, so two states in the same nucleus which have very different charge radius, so different deformation and shape coexistence. Now to the spectroscopy of excited states, so the shown here is the energy of the first 2+ state as a function of neutron number, and the sudden onset of deformation at neutron number 60 is shown by the huge drop of the energy of the 2+ state from above 1 MeV to a few hundred keV. And again, this is only visible in zirconium and strontium, that you have this sharp drop. In krypton, you have a much smoother, more shallow transition. And in the BOV2 value, you see the opposite. From zirconium 98 to zirconium 100, you have this jump in the transition strengths, where you go from single particle, few Weisskopf units, to strongly collective, around 100 Weisskopf units. And again, molybdenum, krypton, this is much more smooth transition. And the R4-2 ratio, which we have discussed before, shows the same behavior, that you have around or less than 2 for the semi-magic zirconiums, but then as you reach this neutron number 60, you have this jump larger than 2.5, and then the strontium and zirconium nuclei beyond neutron number 60, they approach this deformed axial rotor limit. In terms of this shape coexistence that I have indicated, is if you look at the same plot, but now also look at the excitation energy of the first 0+ state. So this is an excitation of 0 spin. And in this nuclei is interpreted as a configuration of a different deformation, which comes close in energy to the ground state. So these are here shown by the dashed lines, and you can see in the zirconium in green that this excited configuration drops down in energy and then becomes very close to the ground state. And then the excited 0+ state goes up in energy again, and this is interpreted as a change in configuration. So these two states swap their nature at neutron number 60. And this can also be observed in the BOV2 values, because you see that the BOV2 value for the excited state, so this transition between two excited states, is at neutron number 60, for example, for this strontium 98, very small, while for the ground state it's very large. So that means that the ground state is deformed and the excited state is spherical in this case. So this can be observed in many other observables that we have for these two nuclei. So this plot shows then the zirconium 98. So this is also the one which was measured in the isobar collisions, and its neighbor strontium. You can see that the ground state with the first 2+ state here at quite high excitation energy. This is the signature of a spherical configuration, but then we have this excited band, which shows this characteristic rotational sequence of J times J plus 1, and the same in the strontium. Okay, so ground state spherical, excited state deformed, and then a rotational band on top of it. And then if you just put 2 more neutrons, so you go from 58 neutrons to 60 neutrons, the thing turns upside down. Now the ground state is shown here, and this is the ground state band. So now this one has the characteristic rotational behavior, while the excited 0+ state shows more this regular spacing for its excitation spectrum. And other observables which are indicated here are BOV2 values. So again, we have around 100 for the decay or the transitions within the rotational band. And then also what is indicated here by these transitions between the 0+ state, this is the electric monopole strength, which is a measure or can be interpreted as a measure of the difference in deformation. So a large electric monopole strength means that these two states have very large difference in deformation. So the interpretation is here that by changing from neutron number 58 to neutron number 60, you essentially swap the two minima around, and what was the spherical configuration now was the ground state, now becomes an excited state because this deformed configuration becomes even lower in energy. There was already many years ago a very nice and elegant and simple explanation of this behavior in terms of the nuclear shell model. So this description by Federman and Pitel assumes that you have zirconium-90 as a spherically closed shell nucleus. So all the neutrons fill up the shell below neutron number 50, and the valence space in the neutrons is completely empty. And then you can have excitations where you move two neutrons out of this core into the valence space. And this, due to a strong proton-neutron interaction, leads to an excitation also on the proton side. So the proton-neutron interaction promotes these particle-hole excitations, which lead to more collective behavior, because due to an increased occupation of the proton G9-half, these correlations can result in, or this lowers the configuration of a deformed configuration. Okay. So because you have now, in this case, these open shell and particle holes, you gain correlation energy, which results in an effective decrease of the excitation energy. So this explains the low but not too low excitation energy of this deformed configuration of zirconium-90. But of course, if you add more and more neutrons to that, these promotions to the G7-half and the deformation driving orbitals here is much more easy to come by. You don't have to excite from the core anymore, but you can excite within the valence space. And this results then to in a very dramatic reduction of the energy of the 2+ state, which you can see here, this is similar plot to before, but the 2+ state and the 0+ state, they're essentially around 1 MeV, and then suddenly they drop down to only 100 keV. This is, and once these excitations become very easy because the valence space gets full. This I'm going to skip. Now, in more recent years, this has attracted more and more attention because in contrast to these very schematic and simple calculations involving only a few orbitals, nowadays one can make these calculations employing the full valence space. And in these Monte Carlo shell model calculations, the authors can calculate really this transition from zirconium-98 to zirconium-100, and this onset of deformation is interpreted as coming from the fact that you have this near degeneracy of the levels, which triggers the symmetry breaking and deformation in the nucleus. So you have probably seen these plots before that again describe as a function of beta and gamma, or the Q0 and Q2, the shape of the nucleus, and the color code shows the potential energy surface. And then in this case, these dots here indicate let's say the amplitude of the the wave function or the basis states in the wave state. So you see that the zirconium-98 is predicted perfectly spherical, and then just 2 neutrons more, it's completely deformed. So a nuclear structure can really change dramatically by just adding 2 neutrons due to the proton-neutron interaction. Everything can change. So it would be really, really exciting if something like that could be independently assessed through heavy ion collision. So how about colliding zirconium-100? So this is now my summary. So deformation is not observable, but it affects many observables. We infer beta from measurements of excitation energies, quadrupole moments, and transition rates, but it's always model dependent. Quadrupole invariants provide a more model independent measure, but they are very hard to obtain experimentally because you need to have the matrix elements between all of the state. The questions I have for you is, how does shape coexistence matter? And is there a way to assess the nature of tracks or deformation between rigid or soft? So thank you.
Catherine, I think that this quite late for you, but in case you want to join the discussion in 2 hours, this question can be discussed. But I do have one more question actually. This the zirconium evolution, right? So if you go back to the beta the landscape where you show when you add neutron, yeah, this plot. There's also beta 3. So I wonder, are there some interaction between the beta 3 degree of freedom and beta 2? In a sense, you know, if there's zirconium-96 have a large beta 3, but small beta 2, but then you add 2 neutrons, then somehow it have a large beta 2. What happened to beta 3? Are there some kind of a correlation, interaction between beta 2 and beta 3 in this shell evolution? I mean, I don't know experimentally, are there some information on this?
This is a very interesting questions. I mean, I briefly showed these shell model calculations, which, I mean, they, even in this very large model space, they have difficulty reproducing these 3- state. So if the 3- state is of octopole collective nature, then it's not easily calculable with the shell model. So other models would be probably more appropriate to that. In the sense of what is experimentally known, I mean, you will hear from Magda probably more about their new measurements for zirconium-98. To my knowledge, there's no measurement of zirconium-100 of the beta 3.
So then maybe I think we should finish, but one more thing is the shape coexistence. If I understand it, basically you have long-lived isomer, right? States with a low excited energy. If they are long-lived, I was wondering, like, if in heavy-ion collision, somehow they have there's some excitation, and they will stay there, right? And that they become part of the beam. So
yes,
I don't know the question is like, what is the rate of producing them? And if then once they're produced, they will be long-lived because there's also gamma factor, which is life by a factor of 1,000. So, but I don't know, you know, this zirconium-96, that they have this long-lived isomer state. You said there's shape coexistence. Are there?
Yes, but they don't live so long. This is not given here, but I know for strontium, the lifetime of this guy is nanoseconds.
Mm-hmm. But for example, the golden 197, I think there's a long-lived.
Yeah, so
And
there are, you probably find some cases, but then the question is, how would you populate them in your reactions? And are they really, I mean, what nature of isomer they are? because a lot of these isomers are not isomers because they have a different shape, but because of other reasons. I mean, because of low decay energy or spins or something like that.
Mostly,
So you would need to find a case where it's
most of them are basically zero plus days for even, but they're just excited and
yeah, but then they don't live so long.
no lives. All right, but we have a factor of 1000 in gamma, so that will,
Yes, but then you go from nanoseconds to what? It's still not very long. You need to.
I have seen cases like minutes and even hours, right? That depends on those days.
Yeah.
But okay. But
Yeah, of course. I mean, if something lives milliseconds and you make it longer by a factor of 1000, then it's okay. But if it lives only nanoseconds,
yeah, then that-
not so much longer, a factor of 1000.
okay, so are there questions from Zoom or the room?
Yeah, one more question.
Yeah, go ahead.
So in your slides, you show the one species I've got even. This I also read some materials that zirconium 196 is a potential to study the neutrinalis double beta decay. So in the experimental week, do you think the nuclear structure can affect the neutrinalis double beta decay search?
Yeah, it does.
Does.
Yes.
Deformation plays
Yeah.
plays a big role.
Yes.
That contribute to that sanity, right?
No, it's just like the matrix element of the neutralized beta decay. So it will be favored between states, the daughter and the mother will have same deformation. So if you have different deformation, the nuclear matrix elements for the neutralized specificity is very small. The transition is favored for, let's say, trickle to trickle, or let's say triaxle to triaxle, but it's much smaller when you have different information at the initial time.
So that the understanding of the beta and beta 3, for example, beta 2 will help, right? Will help the matrix element calculation for this.
Yeah, I mean, you have to take into account the deformation.
Yeah, yeah.
I mean, you can ask to Thomas when we, I mean, if you did some kind of calculation, I mean, I did also. But
Yeah, I asked a question. That's because some experiments proposed to use zirconium 96 to search this, even though the abundance of this nuclei is lower. But it's helpful.
yeah, but it's exactly 96 to what? I don't remember, which like 2 units above importance. So the important thing is, I mean, that's different reasons why you want to set a nuclei for the
Yeah, I think for neutrinolis double beta decay experiment, there are so many things like the Q value, the background, and then I mean it depends on the intermediate nucleus a lot. So it's I'm not an expert on that, but the shape has to be taken into account, but many other things as well.
You have two things. You have like the experimental reasons, and theoretically you have to take into account the shape. It's a different thing.
Rupan, have a question?
Hello, can you hear me?
Yes.
Yeah, so thank you for very nice talk. So I have a question regarding this source of nuclear deformation in slide 11, I guess, if I remember correctly. There were mentioned about 3 sources like intrinsic quadrupole moment, electric quadrupole moment, and rotational. 11 or maybe 12. Oh, no, before that, 10. Yes. So these 3 sources contribute to this deformation separately.
These 3 sources,
Like electric, intrinsic, and spectroscopic. Or...
no, I mean this. Okay, this is all the same. It's all this Q0. Here, I just want to make the distinction between the intrinsic quadrupole moment and the spectroscopic quadrupole moment, because I mean, if you have a prolate shape and it's rotating, and you look at it, it looks oblate, for example. So there's a difference of what you observe in the lab compared to what is the intrinsic quadrupole moment of the shape. This is the only distinction here.
So they are eventually the electric quadrupole moment, but
Yes,
distinct by intrinsic or spectroscopic.
yes.
Okay. Thanks.
Okay. Very good. Thank you so much for this very.
Thank you.
So